first afternoon session. And our first speaker is Ashoke, who will talk about marginal stability and n equal 4 Dyon spectrum.
Okay, thank you. Okay, I'd like to begin by thanking the organizers for inviting me here. The title of my talk is Marginal Stability and n equal to 4 Dyon spectrum, and I'll talk about work done in collaboration with these people over here, Navamita Banerjee, Justin David and Dilip Jatkar. Okay, so here is a list of various references of the work that I have done with my collaborators as well as various other relevant papers. Okay, in particular, a lot of our work draws insight from these two papers over here, one by Cardoso, Dewitt, Capelli and Mohawk, and the other one by C. Strominger and In. Okay, so the goal in this talk will be the following. We will try to find exact formula for the degeneracy of quarter BPS dyons in a class of n equal to 4 supersymmetric string theories, and then compare the result with black hole entropy including higher derivative corrections. Okay. And throughout this talk, when I refer to degeneracy, what we shall mean is really an index that counts the number of bosonic supermultiplets minus the number of fermionic supermultiplets, where the statistics of a supermultiplet is defined to be the statistics of the middle helicity state of that particular supermultiplet. Okay. The eventual goal, the eventual motivation for this comes from trying to understand the relationship between the statistical entropy and black hole entropy beyond leading order. The specific models that I will be considering are known as CHL models, and I will consider a class of CHL models based on Z and orbifolds. Okay. The construction of these models begins with heterotic string theory on a 6-dimensional torus, which I will denote by a product of T4 and 2 circles. And then we take an orbifold of this theory by a Zn group, which is generated by a 2 pi over n shift along one of the circles, which I will take to be S1, together with an order n internal symmetry that preserves n equal to 4 supersymmetry of this model. Okay. And as a result, the orbifold theory will also be n equal to 4 supersymmetric. There is a dual description of these models which will also be very useful for us, and here we begin with type 2b string theory on K3 times a product of two circles S1 and S1 tilde, and again we take an orbifold of this theory by a Zn group, which is generated by 2 pi over n shift along S1 together with an appropriate order and internal symmetry of type 2b string theory on K3. And this order and internal symmetry in fact can be viewed as a geometric symmetry of K3. And again, because this is dual to the theory that I described earlier, this theory also is n equal to 4 supersymmetric. We will be focusing on some special choices of this integer n. Okay. In particular, these are prime values of n. N equal to 1 has been included so that we also have, as a special case of our result, heterotic string theory on T6, because n equal to 1 of course means that we are not taking any orbifold. For these theories, one can find a simple formula for the rank of the gauge group. This is the number of U1 gauge fields in the theory, and that is given by this formula 2k plus 8, where k is this number over here. Okay. And you can easily verify that for each of these values of n, this number is in fact an integer. Okay, otherwise it will not make sense. If we set n equal to 1, then we get k equal to 10 and r is equal to 28, which of course is the well-known answer for the number of U1 gauge fields that you get when you compactify heterotic string theory on T6. Now, I should say at the onset that although we shall focus on these classes of theories, the analysis may be generalized for other values of n which are not necessarily prime, and also for n equal to 4 supersymmetric asymmetric Zn orbifolds of type 2a string theory on T4 times S1 hat. So we replace the heterotic string theory by type 2a string theory. Nevertheless, we take the orbifold in such a way that only the supersymmetries coming from the right moving sector are preserved. All the supersymmetries of this theory that come from the left moving sector are projected out by this orbifold prescription. Okay, so that's the kind of theories for which our analysis can be generalized. Now, since these theories have R(U1) gauge fields, the states of this theory can be characterized by r-dimensional electric charge vector, which I'll denote by Q, and r-dimensional magnetic charge vector, which I'll denote by P. If we define by L a matrix with 6 eigenvalues 1 and r minus 6 eigenvalues minus 1, then the heterotic T-duality transformation is generated by a set of matrices omega which satisfy this relation omega L omega transpose equal to L, and which also preserves the charge lattice. Okay. And the action of the symmetric transformation omega on the charge vectors Q and P take the standard form: Q goes to omega P, P goes to omega, Q goes to omega Q and P goes to omega P. Okay. And one can easily verify that in terms of these charges one can construct bilinears which are T-duality invariants, okay, which are denoted by P square, Q square and P dot Q. Okay. So here I have defined these three T-duality invariant combinations. Now this theory also has edge duality symmetry. The edge duality group from the heterotic viewpoint is best studied by going to the dual description, dual type 2B description that I gave, and looking at the T-duality group of that description. And the result is that it is not the full SL2Z group, but it's a gamma 1n subgroup of SL2Z, which consists of matrices of the form ABCD with determinant 1. Okay, A, B, C, D are of course integers because this is a subgroup of SL2Z, but there is a further restriction that A and D must be equal to 1 mod n and C must be equal to 0 mod n. This is what defines the group gamma 1n. And under edge duality transformation, the electric and magnetic charges transform in this fashion. So our goal is to find the degeneracy of dyons of charge QP, and that degeneracy I will denote by dQP. For the toroidal compactification, a formula for this degeneracy was proposed by Dijkgraaf, Verlinde and Verlinde, and additional arguments for this formula that was proposed by Dijkgraaf, Verlinde and Verlinde were provided by C. Strominger and also by Gayotto from two different points of view. Okay. So our goal will be to generalize this proposal to Zn CHL string theories and then to prove the proposal. So I shall describe how this computation is done for a specific class of charge vectors. Okay. And this charge vector is best described in the type 2B description. So take type 2B on K3 times S1 times S1 tilde modded out by this Zn group. In this theory, we take Q5 D5 branes wrapped on K3 times S1, Q1 D1 branes wrapped on S1, and minus K over n units of momentum along S1. This momentum is fractional because of the Zn orbifolding. So this part describes a familiar Strominger-Vafa system in 5 dimensions. But with this, we add j units of momentum along the other circle S1 tilde and one Kaluza-Klein monopole charge along S1 tilde. Okay. And one can identify this simply as a BMPV black hole, a rotating 5-dimensional black hole at the center of tau-naught space. So that's the configuration for which we will carry out our degeneracy calculation. Now when we translate this to the heterotic description, okay, one can easily read out what are the magnetic and electric charge vectors, and from there one can construct these bilinears, T-duality invariant bilinears. And here is the expression for the T-duality invariant bilinears P square, Q square and Q dot P for this particular charge conservation. Now I should add here that even though our original analysis is done for the spatial charge vector using a combination of explicit calculation as well as T-duality symmetry, the analysis can be generalized to more general charge vectors, provided there is a restriction on the charge vector Q, namely it must correspond to electric charge carried by a twisted sector state. Okay, so the result that I will quote is not valid for arbitrary charge vector, but only those for which Q satisfies this condition. And I should also add that P and Q must be primitive vectors of the lattice. That's a further condition. Okay. And the final result for D, when we express in terms of this invariant combination P square, Q square and Q dot P, remains the same. Okay, so I will display what this function is what D is as a function of P square, Q square and Q dot P. So here is a strategy of how we do the computation. I will not have time to describe the full details. Okay. So we work in the weakly coupled type 2b description. Okay, and in this description, the low energy dynamics of the system is described by three weakly interacting pieces. First of all, we have a piece that describes the closed string excitations around the Kaluzak-Klein monopole. Then we have the dynamics of the d1, d5 center of mass coordinate in the Kaluzak-Klein monopole background. This is the second piece. And finally, we have the relative motion between the d1 and the d5 brane. Okay. Now this part is a well understood system that appears in the 5-dimensional black hole. Okay, and it was analyzed in detail by Dijkgraaf, Moore, Verlinde and Verlinde. The new parts are contribution from these two sectors. Okay. So if we take the limit when the coupling in the type 2b description goes to 0, then we can make these three pieces non-interacting. Okay. And in this limit, the generating function of the spectrum of BPA states is given simply by the product of the generating function of each of these three different systems. Now I should add at this stage that even though the three pieces are mutually non-interacting, individual pieces can be interacting. Okay. For example, the d1, d5 system does bind strongly to the Kaluzak-Klein monopole, and hence to study the dynamics of d1, d5 center of mass motion in the Kaluzak-Klein monopole background, we have to look at a strong coupling quantum mechanics problem, okay, and solve it, okay, and put that result in the expression for the partition function. So now I put the final form of the result of the generating function that you get by taking this product of these three different contributions. Okay. This can be written as 1 over phi k, which is a function of three complex variables rho, sigma and v. This is a known function. It's a little complicated, so I'll describe this only at the very end of the talk. Okay, but let me just say at this stage that this is a known function. Okay, and it transforms as a modular form of weight k of a subgroup of the modular group of genus 2 Riemann surfaces. The precise relation between this generating function 1 over phi k and the degeneracy is given here. So what we do is that we first define this coefficient g, m and p by its triple Fourier expansion, okay, by the triple Fourier expansion of 1 over phi k in powers of e to the 2 pi I rho, e to the 2 pi I sigma and e to the 2 pi I p. The coefficients are called g, m and p, and then the degeneracy d is given in terms of this coefficient g, m and p by evaluating g at half p square, half q square and q dot p. Okay. Now notice in this expansion that the sum over m and p run over integer values and sum over n runs over integer over capital N, okay, and this reflects an asymmetry in the charge lattice for the magnetic charge vector p and the electric charge vector q. Okay. So half p square and q dot p are quantized in integer units, whereas half q square in this case is quantized in units of 1 over capital N. Now there is another subtle point that I want to point out here. Okay. If you look at the expansion of phi k, 1 over phi k, it is important how you do this expansion in order to define this function coefficient g. Okay. In particular, the order of the expansion must be as written here. So first we expand this in powers of e to the 2 pi I rho, okay, in positive powers of e to the 2 pi I rho, because m is bounded from below. Then the result we expand in positive powers of e to the 2 pi I sigma, because n again is bounded from below, and finally we expand the result in powers of e to the 2 pi I v. Now you notice that whereas m and n are bounded from below, I have not said anything about p, and it turns out that the last stage of the expansion, okay, when you expand for a fixed m and n, when you expand the result in powers of e to the 2 pi I v, you have a choice of either expanding in powers of e to the 2 pi I v or in powers of e to the minus 2 pi I v. Okay. These two define two different sets of coefficients g, m and p. Okay. And which one might ask, which one gives the correct g, m and p, which particular expansion gives you the correct g, m and p. Okay. And the answer turns out to be that both of these give rise to the correct g, m and p in a sense that I will make clear later. Okay. But at this stage I just wanted to point out that there is an ambiguity in defining g, m and p by this expansion because of this ambiguity in stating whether the expansion is in positive powers of e to the 2 pi I v or negative powers of e to the 2 pi I v. Now we can equivalently describe the result as a Fourier expansion, okay, as a Fourier integral. So this is the representation of D as a Fourier integral. Okay. Now normally of course the Fourier integral is taken over the real values, and indeed the integration over rho, sigma and V are along the real coordinates. But we choose the imaginary parts of rho, sigma and V. They are fixed, but we choose the imaginary parts of rho, sigma and V in such a way that the Fourier expansion of 1 over phi k that I wrote down in the previous slide is convergent. Okay, only in that case this result is equivalent to what I described earlier. Now since the expansion in rho and sigma are in parts of e to the 2 pi I rho and e to the 2 pi I sigma, we can make those expansions convergent by taking imaginary part of rho to be large and positive and imaginary part of sigma to be large and positive. That's what I have done here. But because there is an ambiguity in whether to expand this generating function in parts of e to the 2 pi I p or e to the minus 2 pi I p, the imaginary part of v, okay, depending on that expansion, should be chosen to be either positive or negative. Okay. So at this stage then the sign of M3 is ambiguous, okay, and the choice of sign of M3 is related to whether we expand 1 over phi k in positive or negative parts of e to the 2 pi I p. Okay. And as we will see later, both signs are relevant, okay, and describe the counting in appropriate regions. Okay, so let me then turn to a slightly different topic, walls of marginal stability. Now we know that the moduli space of n equal to 4 supersymmetric string theories has walls of marginal stability, okay, and these walls of marginal stability are codimension 1 subspaces on which a quarter BPS dion becomes marginally unstable against decay into a pair of half BPS states. And across these lines of marginal stability, typically the dion spectrum can change. Now since we carried out our counting in the weakly coupled type 2B string theory, that means that our results are valid in certain regions in the moduli space which correspond to the weakly coupled type 2B string theory. Okay, so we cannot expect that our results are valid everywhere in the moduli space. It's only valid in certain region in the moduli space. And one can ask, how does the degeneracy change as we move away from this region crossing various walls of marginal stability? Okay. And although we cannot do our counting directly here, we can get an idea of how the degeneracy formula changes by requiring that the final formula is invariant under S duality transformation, because we know that the theory is S duality invariant, okay, under this gamma 1 n subgroup. So here I'll first quote the results for the walls of marginal stability where the walls are, and then I'll describe how the degeneracy changes as we move across these walls. Now for a fixed charge vector QP, there are of course many defined walls, and these defined walls correspond to the possibility of the decay of the state into various pairs. Okay. So if QP breaks up into Q1 P1 and Q minus Q1 P minus P1, then the walls of marginal stability are obtained by requiring that the BPS mass formula will match on the two sides. Okay. And here, because the final states are a pair of half BPS dyons, we require Q1 to be parallel to P1 and Q minus Q1 to be parallel to P minus P1. Okay. Now these mass formula of course have hidden dependence on the asymptotic moduli, okay, and so what this gives is some constraint on the asymptotic moduli for fixed QP and Q1 P1, and it turns out that when a quarter BPS dion is marginally unstable against decay into a pair of half BPS dyons, the corresponding subspaces are codimension 1. Okay. So these describe codimension 1 subspaces of the asymptotic moduli space, and that's why we call them the walls of marginal stability. Now let us denote by A and S the heterotic axion-dilaton modulus. So A is the scalar field that you get by dualizing the NS sector two form field, and S is the exponential of the dilaton field, okay, which measures the inverse string coupling square. So these parameterize the upper half plane or SL2 or mod U1 manifold. Okay. And here are the results that one finds for the location of the walls of marginal stability. So if we fix all other moduli, then one finds that the walls of marginal stability for a fixed set of charges are either circles or straight lines in this upper half plane. The second point one finds is that these curves, these circles and straight lines, never intersect in the interior of the upper half plane. Okay. They can intersect on the real axis, but only at rational points. Okay. And this means that if you are trying to identify various regions or various domains which are bounded by these walls of marginal stability, then those must have vertices at rational points or at I infinity. Okay, why at I infinity? Because two straight lines can meet at I infinity, or they can meet at rational points, because that's what this analysis tells us. So next question is, how does the degeneracy change as we move across these walls of marginal stability? And as I said, this can be figured out by requiring S-duality invariance of the degeneracy formula. What one finds is the following results. One finds that the degeneracies in different domains are given by the same integral formula, but with different integration contour C. Okay, previously I gave the integration contour, okay, where imaginary parts of rho 1, rho and sigma were fixed, imaginary part of V was also fixed, but other at positive or negative values. Now there are more general integration contours that one has to use, but the integral formula is exactly the same in all domains. Now, since these are different contours of integration, we can try to deform one contour into another, and as we do this, we pick up residues from the poles of 1 over phi k. Okay. And these residues from the poles then reflect the change in the degeneracy as we move across the walls of marginal stability, because as we move across the walls of marginal stability, the integration contour changes. And finally one finds that the net change across a wall, the net change in degeneracy across a wall, is proportional to the product of the degeneracies of a pair of half BPS dyons into which the original dyon could decay on that particular wall. Okay, this is what one finds by evaluating the residue of this integrand at various poles. So here I have given an example of these two of these domains in the n equal to 1 case, namely for heterotic string theory on T6. Okay. So both of these regions lie in the weakly coupled type 2B moduli space. Okay. And now we see that in this region we have one particular choice of the integration contour where imaginary parts of rho and sigma are of course always positive, but the imaginary part of V is positive here. Okay. As we move across this wall, the contour changes, the imaginary parts of rho and sigma remains positive, but the imaginary part of V becomes negative. Okay. So the two possible ways of expanding that 1 over phi k correspond to the degeneracies measured in this region and this region. Okay. As we move across this wall, there is a jump in the spectrum, okay, which you get by evaluating the residue from the V equal to 0 pole, and in this case one can find a very physical interpretation of where this jump comes from. This jump in fact comes from a jump in the spectrum in supersymmetric quantum mechanics. This is the strongly coupled supersymmetric quantum mechanics that describes the d1 d5 center of mass motion in the Kaluza-Klein monopole background. Okay, this quantum mechanics problem was solved by Chris Pope in the late 70s and were used by these authors for a completely different purpose, namely to study spectrum of half BPS dyons in n equal to 2 supersymmetric Yang-Mills theories. And there are of course many other domains that I have not shown here, and in these different domains we have completely different choices of the three-dimensional integration contour C. Okay, so now we turn to the problem of comparing this answer to black hole entropy, and to do this comparison what we need to do is to estimate this degeneracy for large charges, because black hole entropy of course is calculated for large values of electric and magnetic charges. And this is done in two stages. First we carry out the V integral by picking up residues from the poles of 1 over phi k. Okay. And the result of doing this integral can be represented as an integral over rho and sigma, because the V integral is already done, and let's call the integrand as e to the minus f for some function of rho and sigma. Okay. the next step is to do the rho and sigma integral using saddle point approximation. Okay. Now this of course can be done, saddle point approximation is well understood, but it is convenient for our purpose to set up the calculation in a slightly systematic manner. So what we do is that we treat this integral as if this is a path integral in a zero-dimensional quantum field theory. Okay, the action being f of rho sigma and rho and sigma are the zero-dimensional fields. So in this approach, then we can define the notion of a 1 pi effective action, which are denoted by minus gamma. Okay, rho and sigma here are the classical fields. Okay, and it's easy to see that if we define a 1 pi effective action from this integral, this path integral, then log d is nothing but the value of this 1 pi effective action, or the negative of the 1 pi effective action at the extremum, at its extremum. Okay. So this 1 pi effective action then can be calculated by the standard Feynman diagram expansion, and it turns out that the loop expansion parameter here is the inverse charge, and this is precisely what we want if we want to compare our answer with the black hole entropy. And the final statistical entropy calculated to one loop order, okay, in this sense, which is obtained by extremizing this 1 pi effective action gamma to one loop order, agrees with the black hole entropy that you get after taking into account the effect of Gauss-Bonnet term in the effective action. Okay. And I should add here that both sides involve complicated expressions involving netic and eta function, and the match is somewhat non-trivial. Okay. So just to show you this, here I have given the 1 pi effective action to one loop order, okay, in terms of a new set of variables a and s, okay, which I have defined here in terms of rho and sigma. Okay. This coefficient psi k is a complicated function which involves netic and eta function, as you can see here, and this answer that you get here, as I said, is exactly the same that you get when you do the calculation from the black hole side using the entropy function formalism. Okay. And from that approach, this is the contribution from the two derivative terms, okay, and this is the contribution from the Gauss-Bonnet term. Okay. A and S in this approach are the near horizon values of the axion and the dilaton field, okay, and of course from that from the black hole side we have to extremize with respect to A and S, because these are the near horizon values and the equations of motion requires us to extremize this with respect to A and S. Okay. We see that, okay, so this coefficient there on the black hole side appears as the coefficient of the Gauss-Bonnet term. Okay. And we see the various netic and eta functions which appear in the coefficient of the Gauss-Bonnet term, and this is the holomorphic anomaly part that also appears as the coefficient of the Gauss-Bonnet term in the effective action. Now, given this, one can ask, what is the role of the walls of marginal stability in this comparison? Okay. Now, it turns out that in the large charge limit, the change in the degeneracy across various walls of marginal stability is exponentially suppressed compared to the leading term. Okay. And as a result, we would expect that the asymptotic expansion of the black hole entropy should not change as we move across the walls of marginal stability if the black hole entropy has to agree with the statistical entropy, because the statistical entropy doesn't change except for exponentially suppressed terms. And this of course is consistent with the generalized attractor mechanism, which tells us that the black hole entropy is independent of the asymptotic values of the moduli parameters. Nevertheless, there is an exponentially suppressed change in the degeneracy as we move across walls of marginal stability. And one can ask, is it possible to explain this on the black hole side? Now it's clear that as long as the attractor mechanism holds, there is no way to explain it on the black hole side, okay, in terms of a single-centered black hole, because the single-centered black hole entropy by the attractor mechanism is strictly independent of the asymptotic moduli. But it turns out that it can be explained by taking into account the contribution from two centered small black holes. Okay. In particular, on the black hole side, what one finds is that as we cross a wall of marginal stability, a particular two-centered black hole can either appear or disappear, okay, and as a result, this causes a change in entropy. Okay, it's not the change in entropy of the original one-centered black hole, the single-centered black hole, which of course remains unchanged, but this is an additional contribution to the degeneracy that comes from these two-centered black holes, and these exist typically on one side of the wall of marginal stability and not the other. Okay. And what one finds in this computation is that this change on the black hole side is precisely in accordance with the prediction of the exact formula for D. So here is for the future. Given the exact degeneracy formula, it is easy to expand the answer for the statistical entropy to include higher parts of inverse charges as well as exponentially suppressed terms. Okay, the calculation on the statistical side is reasonably straightforward and it can be done to any order that you like. The real question is, how does one do the corresponding calculation on the black hole side, and so that one can compare with the result for the statistical entropy. So this is more or less the end of my talk, and as promised, I'll just put up the answer for phi k, which as you can see is a little complicated, and I'll end here. Thank you.
Thank you. Any questions?
Is there some intuitive reason that we need two-centered black holes and not three-centered black holes?
Okay, three-centered black holes will be codimension higher than 1, because as you are moving in the moduli space, the relevant regions are walls which are codimension 1.
Well, once you say that sum of the black hole entropy counts two-centered black holes, then you should cross walls in the moduli space of two-centered black holes.
That is true, yes. Okay, you can cross walls in the moduli space of two-centered black holes, but because they are, so in the full moduli space there is a codimension higher than 1. Okay, and as a result, one expects that as you cross those walls, the degeneracy should not change. Okay. Now, that may sound a little surprising because, one expects that the three-centered black holes will have some effect, and what I suspect is that the reason that we don't see this here, okay, from this continuity argument, is because we are really calculating an index. Okay. The three-centered black holes probably contribute to the degeneracy in a subspace of the moduli space, but they don't contribute to the index because they don't occur in a region in the moduli space. They occur only in some subspaces.
I see. Thank you. So the two-centered black holes are generic?
Yeah, two-centered black holes are generic. They exist in certain regions in the moduli space.
Okay, but three-centered ones only exist.
Okay, I'm not sure if they exist, where they exist, but at least the walls which you have to cross to go to the three-centered black holes can be avoided in the full moduli space. So they cannot contribute to the index because you go from a place where there is no three-centered black hole to a place where three-centered black hole exists without going through any wall of marginal stability.
Was it Phil?
When you compared to the with the higher derivative corrections, you included a term that was just the Gauss-Bonnet term.
That's right.
Do you have an understanding of why that term is enough, or why there are no further contributions from other terms of the same order?
Yes, I have no real understanding as to why that is exact. Okay, we know that in certain limit that becomes exact. Okay, in the limit when there is an underlying ADS3. Okay, why it works there again is not clear. Okay, so the only understanding I have is that in certain region we know the Gauss-Bonnet gives the exact answer. Okay, even though we don't have a theoretical understanding as to why it happens. And from this comparison, it would seem as if it gives the exact answer even in this case, because from the statistical side the calculation is absolutely straightforward, and this is the answer from the statistical side.
There's another question over there.
The two-centered black hole has, in general, angular momentum, and I don't understand what happened to this angular momentum, because I mean, single-centered black hole has does not have any angular momentum.
Yes, but so we are counting number of states without fixing the angular momentum. So our ensemble that we are using sums over all possible angular momentum. So it is true that a two-centered black hole has an angular momentum, so there is an additional contribution to the degeneracy formula Q dot P, because Q dot P is the angular momentum, and that in fact comes out precisely in the exact formula. That when you evaluate the residue, okay, that what is the net change as you cross these walls of marginal stability? The net change is the product of the degeneracy of the individual components and a factor of Q dot P, which counts for the degeneracy due to angular momentum. Okay. But we are summing over all angular momentum in our counting, so that's why we don't fix angular momentum.
One more question.
So in our paper, we have seen that the DVB formula and its contour dependency is nothing more and nothing less of the two center bound states of half BPS particles. While on the other hand, we know that there are also two center bound states of quarter BPS particles, and they also have the walls of marginal stability. So our guess is that indeed the DV formula is counting a specific index that doesn't see this, but we're not sure of this. Do you have another explanation of this, or have you thought about it?
Yes, I think that is related also to this, I mean, it's a similar issue as with this three-centered black hole, that in the n equal to 4 theory, the two-centered black holes, the marginal stability marginal stability of a quarter BPS black hole going into two quarter BPS black holes seems to be of codimension higher than 1. Okay. In n equal to 2, it's codimension 1. Okay. But the same black hole when you embed in n equal to 4 moduli space, the moduli space is larger, and it looks like that you can avoid these walls where the two-centered, where a quarter BPS black hole breaks up into two quarter BPS black holes. Okay. And the physical reason is simple. It's just more difficult to align two vectors in 4 dimensions than aligning two vectors in 2 dimensions, right? Which is the n equal to 2 case. Okay. So because we can avoid these walls of marginal stability, okay, my guess is that these two-centered black holes where you have two quarter BPS states again don't contribute to the index, right? Because you can reach them without crossing any wall of marginal stability in the n equal to 4 moduli space. But you cannot do it in the n equal to 2 moduli space.
Okay, I think we should move on now to the next speaker. Let's thank Ashoke again. And then the next speaker is Sandy Trivedi, who will discuss non-supersymmetric